recording. Okay, so what are we talking about today? Today we're going to talk about flux integrals, Stokes theorem, and maybe the divergence theorem if we have some time. If not, we'll finish it on Thursday. Oh, and a reminder, Thursday is going to be mostly a review day. We might talk about divergence theorem for maybe 10 minutes or so if we don't get to it today. Otherwise, it's your guys' time to ask me questions and I'll answer them. So actually come prepared on Thursday with questions, okay? And then we'll answer them. So where did we stop off? Last time we stopped, we had oriented surfaces. So we said an oriented surface is really a surface with two sides, or an orientable surface. So let's put some technical descriptions to that. A surface is orientable if at each point there is a normal vector that varies continuously across the surface S. There's some glare on this, huh? So what this is saying is I have some surface, and as I move my normal vector pen around, it is pretty smooth. It slowly transitions from one way to the other way. So this is orientable, my hand. If we had a Mobius strip, it would not be orientable because at one point it would be a discontinuous jump. So we didn't really define what continuous means in this case, but we can, well, we're not going to, but you can think of it as varying smoothly. No jumps or quick changes, right? If I am close, if 2 points are close, their normal vectors should be pretty close in the same direction, right? Okay, so how do I compute this? Well, given a parameterization R, this is a parameterization of the surface S. We can compute the derivative with respect to U and the derivative with respect to V, right? And U and V form the basis of the tangent plane, correct? So if we have a surface and we have a tangent plane like this, RU and RV are both inside the tangent plane. And they span the tangent plane. And they're not the same direction ever because the surface is smooth. Okay? So if I want to find a vector that is normal to the surface, it should be normal to my tangent plane, correct? How do I find a vector that's normal to my tangent plane? I take the cross product. So what should my normal vector say? N, I'm going to call it N. It's going to be RU cross RV. This is a vector with direction now. It is normal to my tangent plane, and it's facing up according to the right-hand rule. And I'm just going to normalize it by the length. Okay, so this is a vector that is orthogonal to my surface, and it has length 1. Okay? And is orthogonal to S and has length 1. Any questions?
What does that say on the bottom? I can't read it.
N is orthogonal to S and has length 1.
Thank you.
gotta fix this glare. This is an unfortunate setup situation here. That do any better? Not really. But no. Okay. Any questions on n? So this is the normal vector that points, well, in the positive direction, okay? What does positive mean? It's gonna mean up in this case. Positive is defined by our right-hand rule, and in this case, it will be up. If I have a closed surface, if S is a closed surface, then n points outward. So imagine if I have a closed surface, that's an n. These are n's. There's a glare too, Nick. I haven't quite figured out how to do it, how to fix it. Okay. I think I'm gonna try one more thing here. Give me a second. First, I'm gonna stop the share. And then I'm gonna resume recording. Okay, so if we have a surface like a sphere that is closed, this normal vector points outward, right? So how do we get a normal vector that points inward? We take the cross product in the other direction. So at every point, there will be two normal vectors, one that points in the positive direction and one that points in the negative direction. Okay, positive direction here will mean the first variable cross the second variable, then points in the positive direction. Okay, if I take the second variable and cross with the first variable, that points in the negative direction. Any questions on normal vector? There's a very special case, which we should talk about, when S is the graph of a function, i.e. z is equal to f of xy, right? If z is equal to f of xy, then our parameterization looks like this. R of uv is equal to ui plus yj plus f of xyk. And then, sorry, uv. Ru is equal to 1i plus df du k. Rv is equal to 1j plus df dv. Okay. And then the cross product, which is the the cross product, it has a very nice form. So Ru cross Rv is ijk 1 0 df du 0 1 df dv. So it's minus df dvi minus df duj plus plus k. Negative sign wrong. Okay, someone should check my work there.
Shouldn't the second term have a dv in the bottom? You were going from the upper right.
Oh yes, this should have a,
Second term.
the first term should have a u in the okay, let me look at this here. Okay, this is a plus sign. Let's compute this again. I had an error with both terms. So I get I times this minus this times this. So minus df du minus this times this minus this times that. This is right here. J plus K. That's the correct computation there. Okay. So when our surface is the graph of a function, the cross product has a very nice form. And so N is dui minus df dvj plus 1 k over square root of 1 df du squared df dv squared. Okay. And why did I bring this up? Most of the time we'll be talking, most of the surfaces that you think of are mostly graphs of functions. Not all of them. Obviously the sphere is not, the torus is not, but a lot of them are. Okay. So if you have the graph of a function, you can save a lot of time by appropriately using the correct, well, using the shortcut of the formula for the normal vector. Okay. So what are we talking about? We're going to talk about surface integrals over vector fields. First, we talk about surface integrals. Right? We integrate a function over a surface.
So what is n? What did we just calculate?
We just calculated n, which is our normal vector, when the surface is the graph of a function.
Okay.
Right. So we have two kinds of surfaces: ones that have graphs of functions and ones that are not. Pretty obvious. The ones that are not, we cannot use this formula. We got to use this formula here. But
okay.
when it's a graph of a function, we can use this shortcut. Then we don't have to compute another cross product. Okay. So what's the purpose of this? I want to say, well, we want to think about, we want to compute vector fields over surfaces, right? So imagine something like, there's lots of examples, but we'll start with one that's not in the book here, a solar panel. The solar panel is a flat surface, obviously, but it collects energy by absorbing the rays of the sun, right? So we can think of the intensity of the sun rays and their direction as a vector field. Correct? And the energy that's absorbed is the amount of energy that passes through the solar panel. Right? So the amount of stuff, the vector field, is passing through our surface. Right? Anything that gets reflected isn't getting absorbed, obviously. Does that example make sense? So that's one example of the integral of a vector field over a surface. There are many other ones, like electric fields, electric charge. Imagine I have a net, a very, very fine net, and water is passing through it. I can count or record how much water is passing through my net at a certain time. So these are all examples of what we're going to call flux integrals. So let's start defining these here. Surface integrals over of vector fields. I imagine when you guys do your evaluations, I'm going to get A. He has really shitty handwriting. Wouldn't be the first time. Okay. So how are we going to do this? We're going to do this in the same way we always do things. We have a surface. Some surface in 3 space. And I have some vector field that looks like this. And I want to know how much of the field is passing through my surface, right? And so to do that, I'm going to need to have a direction that tells me what through is, correct? Because if...
The direction vector.
Yeah, I'm going to need a direction vector. What is my direction vector here?
The normal one to your
The
surface.
normal one to my surface. That's why I made a big hoopla about 2 directions, right? Because now I'm interested in deciding which way my fluid is flowing, right? So I need to pick a normal vector that describes which way my fluid is flowing. So given a normal vector right here, this is my normal vector. Gotta get a red pen. This is my normal vector, the red one. How do you think I would compute this? All I really need to do is take the vector field, right? See how much of it is in the same direction as my normal vector, right? And then add that all up. The normal vector tells me the direction I need to go. The vector field tells me the direction it's currently going. So if I can find out how much of my vector field is pointing in the direction of my normal vector, I can add that all up to see how much stuff is passing through my surface. Correct? Does that make sense?
But the normal vector will vary from point to point along the surface, correct? So
Correct. The
integrate.
normal vector's length does not vary, but its direction does vary.
Right.
Right? So, but that's a very important point, because imagine, I think I've said this a million times, what happens when I take a really small box? What is the direction of the normal vector there? It's essentially constant when my box is very small, right? And then I can compute how much stuff is going through this very small box, correct? Which is just my vector field compared to my normal vector. And as my normal vector is essentially constant on that small box, it's a pretty good estimate. And as the box gets smaller and smaller and smaller, it gets better and better and better, right? So how do we determine how much of the vector field is going in the same direction as my normal vector?
I'm sorry, can you repeat that one more time?
What quantity describes the component of my vector field in the direction of my normal vector?
Well, would we have to take a smaller surface from the actual surface and then take like that vector field? Maybe consider that direction instead of the entire vector field direction?
We can chop up the surface into small surfaces and add this all up, is what I'm saying. So just imagine we have this tiny box. That's just that I covered pretty much. This little tiny box. This is all I'm caring about right now. How do I determine the amount of my vector field that is in the direction of my normal vector on this small box surface?
Does it have to do something with like tangent planes or something like that?
Way simpler than we've been doing this whole time. What is a dot product? The length of the dot product is the length of the component of vector A onto vector B.
Yeah.
So really simple stuff from back in we talked about chapter 12. That's why we spent so much time on dot products and cross products, because they have really important physical interpretations. right? So the dot product tells us the component of f on n. This is the component of f projected onto n, right? This tells us exactly how much is in the same direction as my normal vector. So I should just be able to integral this up, right? I'm adding it up. Three then says, well, I'm gonna write this thing down. If f is a continuous vector field defined on an oriented surface S with normal vector n, then the surface integral of f over S is, we're just going to, this is the surface integral of, this is what it's defined to be, the surface integral of f over the surface S. And this is, how do we compute it? We take the field, we dot it with the normal vector, and then we just integrate over the surface. This is also called the flux of F across S. This is more commonly, it's how I normally refer to it. Any questions about the definition?
I have a question.
Uh-huh.
So you were talking about having a surface, and you're looking for all areas at which the vector field passes through a surface, a part of your surface, or a point on your surface.
Mhm.
Right?
Yeah, that's what this part is here.
Yeah,
When I integrate, that's saying how much of the vector field passing through all of my surface.
through all of your surface.
Yeah,
But,
that's what this integral does.
yeah, I remember someone saying that not all of your surface, or not all of the, like, the vector field passing through your surface, not all of the points on that surface will have a vector that passes through it, like, parallel, right?
Yeah, so as the surface changes, let's say my my vector field looks like this. It's just a bunch of straight lines like this, right? And they're all parallel, so they look like this. My surface does this, right?
Yeah.
There are some points where the normal vector does not point perfectly in the same direction as my vector field, and there are some points where it does, right? So in those points where the normal vector is not in the same angle, this term right here will be smaller.
Okay, that
Right.
makes sense.
And in the places where they are in the same direction, this term will be bigger, right? That's why I said this term right here, f dot n, tells you how much, a sense of how much of f is pointing in the same direction as n.
Like a percentage of f pointing in n?
Yeah, essentially,
Okay, that makes sense.
right? It's only a percentage in this case because n is length 1. So if n didn't have length 1, it'd be different. But it's not really a percentage also because this can be negative. Because if f points in the exact opposite direction of n, this number is going to be negative. So you can think of it sort of like a percentage, but not really because I'm allowed negative numbers. Okay. Does that make sense?
Yeah.
Okay. So this is a surface integral. How do we compute surface integrals? We just talked about that on Thursday. And if we look back to our notes on Thursday, we had this definition. Recall, let me go look at the definition again. It said integral of some function in 3 variables over the surface is the same as the integral over the domain parameter D, a parameterization R V dA. So you parameterize, you see where the value is in the domain, and you just take the multiple with the tangent vector. Okay, so let's apply this to right here. Dot n ds. This is equal to, well, what is this? This is f dot ru cross rv divided by length of ru cross rv ds. And now we're going to use this formula right here that says this is the integral over the domain of this function, f on my parameterization, times this, or dotted with dA. Note that these two things cancel. Any questions?
Did the ds and the magnitude of the cross product cancel out?
No, not the ds. This thing up
Oh.
here, the magnitude of the cross product cancels with the magnitude of the cross product here. Because I
Okay.
went from here and I used this formula right here.
Am I reading this right? Is it the double integral of f of r of u, the dot product of the cross product of ru times rv?
Yes.
Yes.
So let's put this as this formula here, and then we'll do an example. Okay. Let's find a nice, easy example. Okay, so let's look at here. We're going to evaluate the integral ds, where f of x, y, z is yi plus xj plus zk, and S is the boundary of the solid region enclosed by the paraboloid z equals 1 minus x squared minus y squared, and z equals 0. So what does this look like? I've got this paraboloid. This is the 0 axis, and it looks like this. So this is my surface S. That's the shell. It's the shell of this solid region. Right, any questions?
S is the boundary of the solid region enclosed by the paraboloid.
Yes. So S is so imagine this was one solid thing, and S is just the shell of the outside. Okay? S has two pieces, right? It has the circular piece at the bottom, and then that hat piece, the shell piece at the top. So let's compute the flux over just the shell part first. Okay. Does that make sense?
I've got a side question.
Yep.
Would your flux solely depends on your vector field, like which direction it's going through your
Yep.
object? Okay.
Correct. 100%. So what's the positive orientation here? Which direction should my normal vector point to be positive?
Like vertically up.
Well, it can't be vertically up. It's only vertically up right here, right? It needs to be normal. But as it moves down, it does this, right? What I'm saying is it points outward, not inward.
Yeah. Definitely.
Okay? So we need to keep track of what's positive when we're doing these kinds of integrals, okay? Positive is outward in this case. So here you'll see the vector will change direction slightly, but it's never going to point inwards. Okay? So how do we compute this? We got a formula right here. We're going to separate this into two regions. Split into two regions. We'll do the hat, just the cap. So what is the what's the domain of this region here? What's the parameter domain in the XY plane? What values does X and Y take?
What was that again?
What values do X and Y take here?
All positive ones? Or no?
Okay.
One.
Not,
X and Y. Can we change it into like a spherical coordinate system where you can say it goes from minus pi to pi in that case?
it's not, you don't need to be spherical here. Cartesian's fine. But what I'm trying to say is X is in this domain, this little circle thing, right? So X and Y need to satisfy the equation X squared plus Y squared is less than or equal to 1.
Yeah.
Right? Because when X is 0, when Z is 0, when Z is equal to 0, we have 1 is equal to X squared plus Y squared. Right? That's this circle right here. So X squared plus Y squared need to be less than or equal to 1. So we can be anywhere in here. That gives us that dome shape. Does that make sense? So what do we need to do? We need to look at, go ahead.
We have a defined vector field.
We have a defined vector field that's right here.
We want to know so we want to know how that passes through our solid, but with relation to like the normal vectors on that solid that are parallel to that.
Yes. So what do I need to do to find that quantity? I need to
Parameterize?
find a normal vector, right?
Yep.
I need to find a normal vector first. And this is a parameterization. Sorry, this surface is defined by this graph, right? So there's already a very nice parameterization for the normal vector. Correct? The normal vector is given, we talked about this at the beginning, by I'm gonna write this again. And I know what this is. This is equal to minus d g dx. I said g, I said, yeah, this is equal to g of xy minus dg dy plus k. That's from the beginning of our discussion on surface, the normal vector for surfaces that are given by graphs. Okay. So if we look at our formula, what do we need? We need the vector field evaluated on this parameterization dotted with this normal vector. Correct?
Was it dg dy in both cases?
This should be an x here.
dg on top, I mean.
Yes, it's dg on top because there's only one function here, right? This is g here.
Okay, all right.
I have a question.
Uh-huh.
Talked earlier about the normal vector or something in the opposite direction or negative, and
Mhm.
you talked about switching our. I think you talked about switching RU and RV.
Yep,
Is it true? That would give us a normal vectors that point inwards.
correct.
Okay, cool.
Okay, so this is our RU cross RV. So to compute this, we just need the integral of f on RUV dotted with, we'll do xy here, minus dg dx minus dg dy plus k dA. Okay. So when we take this dot product, what do we get? It just says we take the I component of f and multiply it with this thing, right? That's what the dot product does. And the j component of f and multiply it by this thing. So we end up getting up here the I component of f, y, times dg dx plus the j component of f, x, times dg dy plus the k component of f, z, times 1. Okay? Any questions how we got here? And we'll finish this up. What is dg dx?
The x component of our normal vector, or
What is it? I mean, we should be able to compute it now.
oh dg. Oh.
2x, negative 2x, my bad.
Negative 2x.
Minus 2x plus x minus 2y plus z dA. Okay? So now, the final question, what is the domain we're integrating over?
Solid.
The domain is going to be in the xy plane somewhere.
When z equals 0, like the projection of our circle, so like 1 equals x squared plus y squared.
Yep, but not just 1 equals, right? X gets to go less than or equal to x squared plus y squared, right? So here D is the solid disk.
Less than or equal to 1.
That's all of this stuff right here. Okay. Also, z is 1 minus x squared minus y squared. Because we're on this surface right here. So how would we solve this integral?
We can't see the problem. It's kind of,
Oh,
there you go.
how would we solve this integral here? When d is this disk?
We can convert x squared plus y squared into r.
Yeah, polar coordinates, right? We got a nice disk here. Do this integral in polar coordinates. Okay. We can do polar coordinates there. I'll leave that to you guys. Any questions on what the process was? So what do we need to do first? We need to first find, or get a parameterization, right? And then find a normal vector. And then follow the formula, okay? Any questions? So there's an interesting example of electric flux in the book. We don't have a lot of time to talk about it, so I'm not going to. But it's a good example for cultural enrichment, if you like those physical examples. There are lots of problems in this section. So when you're doing these problems in this section, really try to think about what they mean, okay? Because in practice, when you move out of Calc 3 to go do whatever other stuff you're gonna wanna do, you never, ever, ever need to actually compute these integrals, ever. Computers do them. You only really need to know how to set them up and why you're setting them up, right? So the computer's not gonna know how to parameterize this surface or what surface it's working over. The computer is not gonna know which way is up or down. It's gonna know how to compute integral though. So you have to do all the conceptual thinking and setting up. So when you're doing these process problems, really try to focus on that. Okay. So move to Stokes' theorem. So I am a huge fan of Stokes' theorem. I think it's really cool. So I remember talking about this last Thursday, but I will bring it up again. So let's start with the basics, the fundamental theorem of calculus. Fundamental theorem of calculus. It says integral of f prime of t dt equals f of b minus f of a. Right? So this is one dimensional, one dim, flat. So what does this say? This says I take the integral over the interior of my derivative is equal to the function itself on the boundary, right? And the interior this time needed to be flat. Then we move to the fundamental theorem of line integrals. So I integrate over my curve C. Gradient of f, sorry. This is equal to f evaluated at b minus f evaluated at a. This is one-dimensional, curved. Right, now my curve can do this, and it says the integral over my curve is the derivative. The integral over my curve of the derivative is equal to the integral, no integral of my function on the endpoints. So just keep in mind what we're doing here. We're evaluating the function on the boundary and comparing it to an integral of the derivative on the inside.
The derivative of our gradient of f?
The derivative of our function, whatever our function is. In this case, it's the derivative. In this case, it's the gradient, right? Because it's in higher dimensions. Okay? So then we had Green's theorem. And it said, well, I got a surface, D, a region of the plane, D, and it says, well, the integral of f dot ds is over D is equal to the integral, I'm gonna write, integral over the closed region f dot ds, right now dr. This is equal to the integral over the region D of the curl of f dot k dA. Didn't write that in a good spot. So it says this allows us to talk in 2 dimensions now. This is 2dim flat. It says the integral over the curve outside, the exterior, is equal to the integral of the interior of the curl. Right, so again, focus on, I can take integral over, I'm translating information on being on the boundary to being on the inside. That's what all of these things are doing. Okay? In this case, it was flat, and then we moved it to not flat, and this is flat, and now what do you think we're gonna do? Look at non-flat surfaces. Okay.
Green's theorem, but curved.
Yeah, Green's theorem, but curved. And that's Stokes' theorem. This is Green's theorem, but curved. Okay. So what does Stokes' theorem say? It says, there's a couple things that need to be said here. I'm going to try to write it down. S, be an oriented, piecewise, smooth surface that is bounded by a simple closed piecewise smooth boundary C with positive orientation. There's lots of stuff here. We'll go through it in just a moment. Let F be a vector field whose components have continuous partial derivatives. On S. Then okay. There's lots and lots of adjectives here, so we'll describe them as we go. Okay. First, I want to make the observation that this looks very similar to Green's theorem. Only difference is in Green's theorem, I dotted this with the k vector. Here I'm dotting it with this S vector. Okay, so let's come back to that and let's digest some of these adjectives. Okay, so I've got some surface, it looks like this. Right? It's smooth, it's a one piece, and the boundary, which is this curve right here, boundary C. This is the positive orientation, right? Because if I travel along the curve, my surface is inside, correct? It's to the left of my point. Only one R. Okay. Any questions on that so far? C is nice. It's simple. There's no holes in it. It's not broken. And it's the one smooth thing that goes all the way around. Okay. So S also needs to be oriented a certain way, right? Which way should S point here? What is positive here in this case?
Normal
Opposite
to the
up.
surface.
Yes, the orientation of my surface should go up. That's positive, right? Think about, we're going to stick to the right-hand rule. We're on this, I can do this. We're right here. My curve goes like this, following my fingers, and my thumb points up in the normal vector. So if the curve was going the other way, the curve was oriented in the negative direction, then my surface normal vector would point downwards.
This is a non-flat surface, though.
This is not flat, yes. So you can see it won't be flat as it's a little, think of it like this way. This kind of shape. Okay. So I can compute the integral of f on this curve that's just super not flat, right? It's a three-dimensional curve by computing the integral of the curl on the inside of the surface. Does that make sense?
One more time.
I can compute the integral of the vector field on the outside, on the boundary, by instead computing the curl of the vector field and computing its flux across S.
How?
That's Stokes' theorem. That's what Stokes' theorem says right here. They're saying this is an equality, believe it or not.
So are you substituting the like Z direction with the flux, kind of like with the, what do you call it, with the vector field?
What do you mean the Z direction?
Like,
Z direction where?
I mean, if it's like not flat, then it has a third dimension that goes upwards, right?
True, yes.
So are we substituting here one dimension for another one that's in the same direction? Kind of
Well,
like that?
okay. So yes, it has a third dimension, but the third dimension is inherently 100% dependent on the first two. Correct?
Okay,
Do you agree with that?
yes.
So there's not really a third dimension. The surface itself really only has two dimensions, right?
Yes.
So we don't need to, we're not dealing with it at all.
Okay.
Does that make sense?
I think so, yeah.
We are dealing with, we're taking that into account by dealing with this normal vector that's hidden in this integral.
Okay.
Because that tells us where we start and which way to go.
But to clarify, once again, only two dimensions at any given point, correct?
Yes.
Okay.
Well, The surface as a whole is two-dimensional.
It's an aggregate of two-dimensional patches, right?
Yeah, but that's still two-dimensional, right? I can't add up two-dimensional things to get a three-dimensional object.
True. It's just spread out in 3 dimensions. I get it.
Yeah, right?
Okay.
Okay. Let me say that one more time. The integral of the vector field f across the boundary is equal to the integral of the curl of f across over the surface. So this is another case of what we're doing here that we did here multiple times, right? This is the boundary, and this is the interior. So where Stokes' theorem does what Green's theorem and these other two theorems do, it takes an integral from the inside, the interior, and transforms it to a computation on the outside, the boundary. Okay?
What would S be then?
S is this surface right here.
That's a three-dimensional surface, right?
It's a two-dimensional surface. It sits in 3 space, but it's two-dimensional. Because, I mean, think about this. Think about this piece of paper. How many dimensions is this piece of paper? It's 2, right? If I'm right here, I only have two choices of moving. I can move up on the paper or down along the paper. But I can't move this way. I'm no longer on the piece of paper. Right?
But you drew something that's like a curved piece of paper.
True, but the curved piece of paper still has 2 dimensions. Okay, I bend it like this. It's curved. I can move this way. I can move this way. I can't move up because I leave the surface of the paper.
You mean on the surface?
Yeah, right. Imagine I'm living on the surface. I'm an ant to measure dimension. Does that make sense? Surfaces are two-dimensional. They are embedded in 3 space. You put certain, because we view things in 3 space, but they're two-dimensional. They only have 2 independent parameters.
Can I offer a visualization that may make it a bit easier? If you think of something that's a surface, but oval to begin with, or some odd shape like that, and easily bendable, like a bath mat made out of plastic, or maybe a bath, floor mat in an oval shape. It's always 2-dimensional. Imagine there's no thickness. But you can fold it, you can curve it into any number of shapes over 3 dimensions. It stays 2-dimensional. Does that help or not?
Another way you can view this is looking at it locally. The sphere itself, imagine the Earth. People think the Earth is flat. Not important people, but some people do. Because locally, the Earth is very flat, right? If you zoom in, on the small scale, the Earth looks flat, like a 2-dimensional surface. I can only walk forward and backwards, side to side. I cannot go up and stay on the Earth, correct? But in fact, the Earth is actually round because we imagine patching together all these flat objects in a way that makes the whole global object round. So we can view this 2 dimensions and 3 dimensions as locally 2-dimensional. Because if I am somewhere on the surface of this cup, for example, right here, this is going to look very flat. If I'm right here and I'm tiny, it's going to look like the plane, just like R2. So it has dimension 2. Did that make sense?
Yeah, it makes sense. I guess I'm just confused. By like an orientation point. Like it's just if you're looking at your surface from a third-person perspective, clearly there's going to be some change in elevation and like and in your x and y directions?
If you're looking at it from, so now we are looking at this surface right here from an outside standpoint, right? But if I'm looking at it from an outside standpoint, for me to appropriately decide which is up and which is down, I need to decide which way the curve is going as well, right? So when I'm here and I'm looking at it from outside and I know the curve is oriented this way, this tells me which way it's up already. This way, up is this way. Since I am extrinsic to this object, I have to have an orientation to determine up and down. Okay? So this is Stokes' theorem. Let's see how it compares to Green's theorem. Okay? So let's think, what happens if my surface here is not up here and curvy, but it's actually flat?
Like a projection?
Yeah, assume S is flat. Okay. So what happens now? If S is flat, what is my what direction is my normal vector pointing in? In fact, what is the normal vector? If I have a flat surface like this, where is my normal vector pointing?
Straight up?
Straight up. And how do I describe that in terms of a vector? Okay.
Cross product?
This is the vector that points straight up of length 1, right? Does that make sense? You're muted, Darius.
Okay, so I'm just walking through it really slowly here. Your upward vector is positive,
Yep.
and you have your flat shape. I'm going to get when I see an example.
Okay. So we'll look at an example in just a moment here, but I want to say I'm on this piece of paper right here, and up, the positive direction is up. Which way should my normal vector point? It should point directly up, right? It should have no x or y components at all, correct? It only should have a k component, right?
Yep.
And the vector needs to have length 1. So what should its k component have length? What should the coefficient for its k component be? 1.
Okay.
Right? So when we know the normal vector, we have that this integral S of the curl of f dot ds, this is equal the integral, excuse me, of the curl f dot the normal vector ds, right? And the normal vector is just k in this case, which gives us Green's theorem. Dot k ds, Green's theorem. What I'm trying to get at in this description is Stokes' theorem is a generalization of Green's theorem. If the surface is flat, we get Green's theorem back. If it's not flat, then we could use Stokes' theorem. We'll see that in some examples in a moment. But I really want to emphasize all these theorems are the same. They're essentially duplicates of each other in the concepts, not computation exactly, because one's in 1 dimension, something's in 2 dimensions, that's not the same. But the concepts are the same. Okay? Let's look at an example here. Let's evaluate integral C f dr, where f of x, y, z is minus y squared I plus xj plus z squared k. Okay. C is the intersection of the plane y plus z equals 2 and the cylinder x squared plus y squared equals 1. Orient C counterclockwise. Counterclockwise. Okay, let's try to draw a picture here. My cylinder looks like this. My plane looks like this. So I'm just chopping off this bit right here. Right here. So it looks like, draw a great picture. It looks like this cylinder where I lob off that corner piece. Okay? So I want to compute the integral of the vector field on the curve, which is this part that it intersects. Does that make sense? No? Yes?
It'll come to me. I'll see.
I mean, the book has a nice picture of this. They draw really nice pictures here. So let me just zoom in.
Is this 16:7? I'll go find it real quick.
Yeah, I have it right here. I'm just going to draw a picture here. I'm going to show you this picture because it's much nicer than mine. Right here. Right, it's a cylinder. They lobbed off the top of it. It's oriented this way. Okay? Any questions?
I have a slight question.
Uh-huh.
It kind of makes, well, it makes an ellipse, right? By cutting it
Yeah,
off.
it makes an ellipse, the top part. Correct.
Is it possible to create the equation of that specific ellipse by using the x squared plus y squared equals 1 and y plus z equals 2?
Yes. You could do that.
Would that help us at all, or is that just nonsense?
I mean, does it help us? We don't need to, but that's not a bad idea. Because we are going to essentially do that, but not really do that. I'll explain to you what I mean by that in a moment. Yes, that's going to be useful to us, but we don't need a specific equation for that ellipse. Okay, so we're going to try to use Stokes' theorem here. And we could compute this directly like we did before, right? We take a tangent vector. So we could do this directly by parameterizing this curve, C, right? And then taking its tangent vector and then doing all the other stuff we did before, right? But instead, we're going to use Stokes' theorem. And Stokes' theorem is going to want us to, I'm going to take a picture of this. This is a nice picture. 1 second. And so Stokes' theorem says that, I can't zoom in here. Okay. So instead of computing this line integral directly, I'm going to compute the surface integral. And I pick my surface as this ellipse, which Nick was talking about right here. Right? So it will be useful to us to know the equation of this ellipse, because that's going to be the surface I chose. Note, there are many surfaces I could pick that have this C as its boundary, right? I could pick the bottom part of this if I wanted, the bottom part of the cylinder, and make it smooth, like this, and it has the same boundary as C. I could pick something that goes up here. I could pick some weird stuff that does this, and comes out here, and then comes back in here. And this is its boundary. Okay, so I can pick lots of different surfaces that have the boundary of C. I'm going to pick the very easy one, which is this ellipse. Okay? And so now I'm going to compute this integral. So I have f. I have to go find the curl, right? So we should remember how to compute the curl. How do I compute the curl?
Was it like F cross the
The gradient
Gradient.
cross the vector.
Gradient operator.
Yeah, the gradient operator across the vector field, right? This is I, J, K, ddx, ddy, ddz, minus y squared, x, z squared. And then this gets you 1 plus 2yk if you do the computation there. Okay? So now we've got our curl. What do we need to do to compute this integral? We need to find a surface, which we just picked our ellipse, right? And an equation that describes our surface. So we need S and a parameterization. So S is going to be this picture that Nick said, this ellipse right here, right? So what is the ellipse there? The ellipse is defined by this equation, the ellipse, did I spell that wrong? Right, who cares? Is defined by Z is equal to 2 minus Y, right? And x squared plus y squared is less or equal to 1. So these two equations define our ellipse, correct? And so this integral is the integral of d over 1 plus 2y dA.
And what is D?
What is d? D is the information in the xy plane, right?
Okay.
And what are the constraints on the xy plane? Right here.
Ah, okay.
Right? D is, as the picture says,
Region.
this area, this region right here. Okay. So another circle, we should do polar coordinates. Okay. Any questions? Yes?
I have a question.
Yep.
Earlier you talked about like projecting our curve onto the XY axis.
Mhm.
How
Our
come
surface.
our surface, we're projecting our surface onto that axis? We're not really doing anything like that, it seems, right here.
Well, we didn't do anything like that earlier, but if we're only interested in looking at the domain changes, XY changes, right? And if we sat up here and had a flashlight, oh, you can't see this. If we were up here and had a flashlight and shined right down, the x squared plus y squared equals less than or equal to 1 would be the projection of this ellipse onto the xy plane.
Okay.
So we don't need to, we are doing a projection, but we don't really need to view it as a projection because we're just taking the inputs right here, sorry, the inputs, the xy components of the surface.
The boundaries, essentially.
Yeah, but also inside, right? We're looking at our surface projected down to the xy plane. Okay. Any other questions? No? Okay. So one thing I want to point out, which is really, really cool about Stokes' theorem, is what about different surfaces? So given F and two surfaces, S1 and S2, I have two surfaces, S1 and S2, that satisfy Stokes' theorem. So let's say and have a common boundary. Let's say I have this curve right here. It's like a nice circle thingy. And S1 is the inside. It's this flat disk. Okay. S2 is then this weird hat thing. Okay. I have two surfaces. They're both smooth. They're both, they're both smooth and oriented the correct way. What is the integral FDS on S1 and integral FDS on S2? How do these two numbers compare?
I'm confused about the question.
So this is a number, right? It's the flux of the vector field across the surface S1. And this is the flux across the vector field across X2. How are these related?
Question, is S1 a part of S2?
No.
Okay.
So imagine it like this. I have a coffee cup with no handle, right? The curve is just the rim. S1 is the flat part right here, which I don't have a picture of because there's a hole there. And S2 is the rest of the coffee cup.
Oh, okay.
So S1 is this part, just this flat circle disc. Imagine I have a disc on top of this, right? And S2 is the rest of the cup.
Okay.
Does that make sense?
Kinda.
So do we see that the surfaces are different?
Yeah.
And they're very different, right? Now I want to know, what is the flux across each of them?
Wouldn't the flux going to the first one be equal to the one going to the second one?
Yeah.
Why?
I mean, I don't know if you got stuff
Small
passing through that
surface.
first one.
Are they both level parallel to each other?
What does that mean?
I mean, if they both are like across the same surface, the flux should technically be the same if you're taking a small.
But they're not the same surface. They're very different surfaces,
Okay.
right?
Mm.
So I should have drawn a picture of this better, but they're very different surfaces. So S2 is all of this coffee cup, except for this handle. The handle doesn't count. But imagine this whole cup surface. And S1 is just this small little ring, a disc, a small disc right here.
Yeah.
So they're very different surfaces.
I feel like anything that passes through S1, because S1 is smaller than S2.
Uh-huh.
So anything that passes through S1, like a vector field that the vectors are normal to or parallel to the normal vectors on S1, that whatever passes through S1 has to be what goes through S2. No?
Possibly, but what if the vector field is different up here? It never passed through X1 up here. Do you see this cup? So, do you see the cup?
I see the cup now.
So, if my vector field is really strong right here, right? It never passes through X1 because S1 is up here and it's going this way. It only passes through S2. I mean, the answer to this is they are the same, but
Well, why?
Stokes' theorem says they're the same. And what does that mean? They have the same boundary. They both have this boundary curve as C. Back to the coffee cup. They both share this boundary curve right here. So Stokes' theorem says it doesn't matter what happens on the inside of the surface. This surface could look completely different. It could be all the way down here and look like an upside down mushroom or whatever. It does not matter what this surface is or the top surface is. All that matters is the boundary is the same.
You mean the boundary at which the vector field is passing through?
The boundary of the surface, as in this curve right here. The vector field is passing through everywhere, right?
Okay, wait. All right. I'm confused. So like, I've got a coffee cup right here,
Uh-huh.
and this is the S1 that you're talking about, yeah?
No, this is the curve. S1 is what's inside the circle. Imagine I have this piece of paper. It's laying on top of this coffee cup. Do you see the coffee cup?
I can't. It's too low.
Do you see the coffee cup now? I'll put it down here. This makes more sense. S1 is that. This whole thing is S1. Right?
Okay.
This thing right here is the curve,
All right.
boundary of S1. Everything else is S2.
But if they only share one curve, how can you say they have the same boundary?
No, they share, well, that is their boundary, right? Because this is their curved boundary. So imagine this is smooth at the bottom. We can see that when I put the paper back on here, what's the boundary of this curve? It's this right here, right?
Yeah.
Sorry, what's the boundary of this surface? It's just this little circular curve right here, right?
Yeah.
Do we agree with that?
Yeah.
Now, what's the boundary of this thing? Well, down here, it's still smooth and in one piece, right?
Yeah.
So how do I get to the end? I only really get to the end when I come up to here,
Huh.
right?
Can you repeat that again?
I only really get to the end of the surface or the boundary when I'm up right here.
Yeah.
Because when I'm down here, I can keep going, right? There's no boundary yet.
Exactly.
The only time I get to the boundary or the end is when I'm right here.
Okay.
So this is the boundary, and it's the same curve as the boundary when I had an S1.
But how does that relate to the? So you said that S2 is everything that's outside, right? Like if you said the S1 is the coffee cups inside, the outside would be That's S2, right?
So let's be clear here. S1 is not this stuff inside here.
The top is,
S1 is only this top layer.
yeah.
Yes.
But S2 in this case is,
S2 is all this stuff over here on the outside and the
Okay.
stuff on the inside.
Okay,
Oh.
that makes sense.
okay, okay.
But what are you saying then?
I'm saying that since they share the same curve as boundary, this curve, the flux across this very simple surface, the circle, is the same as the flux across this whole weird surface, the cup.
How?
I can understand that in the context of the coffee cup because it kind of makes sense. But in the drawing though, like the things you drew in red, that is not a part of S1. So how can they both have the same boundaries? Kind of what I'm.
It is. I imagine that this is where they join. So imagine the exact same kind of picture, except instead of my coffee cup looking smooth down here, it's this weird little blobbish shape.
Okay.
It does this stuff.
It could have been just a straight.
You muted yourself halfway through that conversation.
It could have been just a straight cylinder too.
It
Like,
could have been just a straight cylinder. Well, it couldn't be a straight cylinder because the boundary will be at the bottom there also.
okay, well, yeah, I guess, yeah.
Because if it's a straight cylinder, you're adding more points to the boundary. Well, maybe it could be a cylinder if we put a cap at the bottom.
Yeah, like something, it could be a very simple shape.
Yeah,
I
it
guess is
could
what
be
I'm
like this
trying to
beaker
say.
shape.
There you go, yeah. That, like, just like that.
Yeah. It could be like a pill bottle shape. But the thing I'm trying to make a point is that one of those shapes is really hard to integrate over, right?
Mhm.
That
Yeah.
weird cup shape. One of those shapes is really easy to integrate over. The circle.
Yeah.
And they have the same flux because they share the same boundary.
Okay.
That's the part that confuses me. How do they have the same flux?
Because Stokes' theorem says that the flux of the curl is the same as the vector field over the boundary.
Stuff
Okay.
on the outside and stuff.
Yeah,
So if
right.
they have
So
the same vector field, the boundary is the same, then the flux is the same.
yes,
Okay.
if they're the same vector field and the boundary is the same, no matter what the surfaces are, as long as the boundary is the same, the flux is the same.
Right.
So it doesn't matter what happens on the inside. It only matters what happens on the outside.
Yeah.
And I want to say this is not that crazy because we've talked about this before in basic calculus, right? And why, how? Let's look at if this is f prime. I'm going to try to draw a picture here. Let's say f does this. I can find another function. Oh, okay. Let me think here. Let's pretend that picture didn't exist and we'll draw a better picture. So if we have this integral a to b, f prime of t dt, and we know this is equal to f of b minus f of a, right? So if I have a function that is the same on these 2 points, right? So let's assume g exists and is differentiable with g of b equal to g of a. Sorry, g of b equal to f of b and g of a equal to f of a, right? I pick any other function I want as long as the endpoints match up. Do we understand what we're starting with? We have a function f and a function g that have endpoints that match up. if I take the derivative of g, then integral from a to b of g prime of t dt is f of b minus f of a, which is equal to g of b minus g of a. And this derivative g prime may be very, very, very different than this derivative f prime.
But because they're equal at those
Because they're equal
points.
on the boundary, the integrals are the same. So give me a second, I'll think of a nice example. We can think of these functions in yes, okay. How about this? F of x is x to the 100, right? And g of x is equal to x. Correct? These are two very different functions, right? A is equal to 0 and b is equal to 1. F of 0 is 0. F of 1 is 1. That's the same as g of 0 and g of 1. Correct? What's the derivative of g? 1. So the integral from a to b from 0 to 1 of 1 dt. This is g prime of x, right? And this is integral from 0 to 1 of 100 x to the 99. This is f prime of x dx. These two integrals are the same. Do we see that?
Could you go down a bit?
Oh, sorry. These two integrals are the same. They have very different functions on the inside. But when I do the integration, I see that their boundaries are the same, and these will be the same.
Yeah.
Right, so this is just like what we were talking about for Stokes' theorem. We have some really different stuff on the inside, on the interior, but their boundaries agree, so it doesn't really matter. So remember, if two surfaces satisfy Stokes' theorem and they share the same boundary, their flux of the curl will be the same.
The flux of their curl?
The flux of the curl, right? Because Stokes' theorem says this. Okay. Any questions?
Many.
So I really recommend reading this section. There's a nice example about how curl relates to Stokes' theorem. Do some of the exercises and get used to it. On Thursday, we'll talk about divergence for just a little bit. Divergence is another interesting thing, but 20 minutes maybe, and then we'll do a review. Okay? I don't want to start divergence now because we're going to run out of time, but we can talk about it on Thursday. If you have questions, please bring them up on Thursday or send me an email.
I have a question right now.
Okay.
So earlier you talked about flux, between like that being like the amount of something passing through something. Yeah.
Yep.
So when you took that paper and you put it around your cup, that paper was S1, right?
Yep.
And the boundary where that paper met with the cup was the curve or the
Curve. Yep.
boundary. And then S2 was the rest of the cup.
Yes.
So you talk about how flux or the amount of stuff passing through S1 bounded by our curve is equal to the amount of stuff passing through S2 bounded by that same curve.
Yes.
Okay,
But
that's where I'm confused.
passing through needs to be described as the curl of your vector field. Passing through the surface S1 is going to be the same as the curl of your vector field passed through S2, because that is both equal to your vector field passing through the curve. When I move from the integral to, when I move up and down from the interior to the boundary, I get an extra thing that happens, right? In this case, when I move from the boundary to the interior, I have to take a derivative, right? I have this right here. When I moved from the boundary to the interior, I had to take a derivative. When I moved from the boundary to the interior, I had to do a derivative, a gradient. When I moved from the boundary to the interior, I had to do a curl, right? So
Okay.
when I move from the boundary to the interior, I have to do something. In the two-dimensional case, it's the curl.
I guess it's just kind of hard to think of. We're trying to conceptualize it.
It is tricky to think about. Agreed.
Okay.
Any other questions? Okay, so remember to do your evaluations. And I'll see you guys Thursday. Have a nice day.